Assalamualaikum and a very good day. My name is Muhammad Aziz bin Anas with the student ID 2019582271 and currently under the supervision of TS Dr. Abdul Halim bin Abdullah. Without further ado, I want to start the presentation of my final year project, which I am proposing to study the effects of infill density, wall perimeter and layer height in 3D printing. Content. These are the contents that I will be presenting throughout this presentation regarding the proposal, which will be started with project summary until the project planning to study the effects of parameters and stated earlier. Project summary. To summarize this project, it is to study the effects of parameters in the 3D printing technique, which in this project are infill density, wall perimeter and layer height. There are other parameters in 3D printing like infill patterns, print speed, and fan speed, but in this it will be focused only in 3 parameters. Next is to analyze the model of the different parameters using computational and experimental analysis. Computational analysis is a test using simulation software on 3D model, while experimental analysis is tests using real testing machine on a real specimen model and finding which settings of the parameters have the best balance between the amount of material used, time taken for fabrication, and aesthetic of the strength of the model. Introduction background. Before we delve any further, we have to understand what the title of the project is about. Firstly, what is infill density? Infill density is what makes the structure of the material inside the part, because most of the time, parts that are printed through 3D printing are not fully solid. It ranges from 1 to 100%. The second parameter that will be studied is the wall perimeter. The wall perimeter or shell thickness is the outer cross-section of the layer of the 3D printed parts. It gives the shape of the 3D printed parts. It is generally known that increasing the wall perimeter of the 3D printed parts can increase the overall strength of the parts. The third parameter is the layer height. The layer height is the exact height of each layer of plastic extruded, cured or sintered by a 3D printer. 3D printing is a type of fused deposition modeling, in short FDM. Is a method of additive manufacturing where layers of materials are fused together in a pattern to create an object. Therefore, layer heights determines the surface of the parts, in which smaller layer heights will result in smoother surface of parts. For the literature review, there are certain things that must be researched and studied from the past experiments that are quite similar to our topics. The first one is the material. Through a study done by M. Salim on the mechanical properties on the ABS PLA materials for geospatial imaging printed product using 3D printer technology, I have gathered few information regarding both of the materials that were frequently used in 3D printing. The first material is the acrylonitrile butadiene styrene, in short ABS. ABS is a non-biodegradable polymer, which means it is difficult to decompose and not environmentally friendly material. It is also an inexpensive material that is usually produced in color that is commonly used, therefore not many variations exist. ABS have a higher melting point compared to PLA, and also generally stronger and more durable. On the other hand, polylactic acid, in short PLA, is a biodegradable material when compared to ABS. It has less material performance, but it is produced in various colors. It is easier to control and process due to its lower melting point. PLA is an eco-friendly choice because it does not release toxic fumes when it is processed. After the studies done on both, I have decided to choose the PLA as the material that will be used for the 3D printed specimen. The second concern is about the specimen type that will be 3D model and 3D printed to be used during tensile tests. The type of specimen must be chosen before they are modeled in the CAD software. A study done by J. Laureto states that type of specimen used for the standard tensile method for tensile property of plastic is the ASTM D638. There are 5 types of this specimen, which type 1, type 2, type 3, type 4 and type 5. All these specimens have different dimensions. The ASTM D638 14 type 1 was chosen as a specimen because it has a larger size. The larger size means that the infill pattern will be easy to model in the CAD software, and ideal thickness will be easier to detect with the naked eye. The third concern is on the infill patterns. One of the parameters in 3D printing is infill patterns. In 3D printing, parts that are printed are usually not fully solid on the inside. They are partially hollow with different patterns. This can save the material used for making 3D printed parts. Even though the infill pattern is not the parameters that will be studied, it must be decided early on to act as constants on all the model. Rectilinear pattern is chosen out of all the pattern. This is due to its generally short fabrication time. Rectilinear also has good balance between complexity and strength compared to other patterns. It is the only pattern recommended for 100% infill density, thus makes it suitable for this project. Next, the parameter that will be studied is the infill density. The infill density ranges from 1 to 100%. Therefore, the chosen density must be sequential and close to each other. Generally, the higher the infill densities, the higher the strength of parts. Hence, 5 models will be used and the infill density chosen are 5%, 10%, 20%, 40%, 80%, and 100%. The wall parameter is sometimes referred to as shells, and most of the times, people will use single shell, double shell, and so on. The thicker the wall parameter, the stronger the parts, but uses more material in the process. The wall perimeter chosen are 1 mm, 2 mm, and 3 mm. Layer height is the only parameter that can only be tested with experimental analysis. This is because it cannot be modeled through a CAD software. It can only be set on a 3D printer. It is known that the larger the layer height, the shorter the fabrication time at a cost of a rougher surface of parts. The layer height chosen that will be tested are 0.05 mm, 0.1 mm, and 0.2 mm. For the problem statement, increasing the settings for all the parameters, which is the infill density, wall perimeter, and layer height, can lead to higher strength of parts, but at the same time resulted in more material use and longer fabrication times. Thus, finding the right balance between these factors can save costs and times, as well as having reasonable strength of parts. Plus, mechanical properties of PLA for different parameter settings does not available yet. For the objectives, the first objective is to develop a 3D model of the tensile test specimen at different infill densities, wall perimeter, and layer heights. This will be further discussed in the scope of study. The second objective is to predict the effects the different parameter settings to the strength of the models. For the scope and limitation, scope of study. For the infill density test, there will be 6 models with 6 different infill densities ranging from 5% to 100%. All the wall perimeter will be set at 1 mm and layer height will be at 0.1 mm. For the second test, which is the wall perimeter test, there will be 3 models with the wall perimeter of 1 mm, 2 mm and 3 mm. The infill density will be constant at 10% and the layer height will be at 0.1 mm. For the test of layer height, it will only comprise of experimental analysis only. The layer height chosen are 0.05 mm, 0.1 mm and 0.2 mm. The wall perimeter are kept at 1 mm and infill density at 10%. The 3D model will be shown in the preliminary results. For the limitation of study, the software used to create 3D model is the CATIA V5. Next, the software used to carry out static analysis on the specimen is the abacus. In order to estimate the dimension of the infill density, I have to use the Ultimaker Cura, which is a slicer software. Even though there are more parameters in 3D printing, it is limited to only 3 parameters, which are infill density, wall perimeter, and layer height. These studies are limited to PLA material and rectilinear infill patterns only. For the methodology, there are 7 steps that need to be done in order to finish the overall project, starting from literature study up until the final step, which is the final report. In literature study, the theory behind the project will be studied. The Young's modulus of a material is an unchangeable fundamental feature of all the materials. It is, however, depending on temperature and pressure. When a material has a high modulus of elasticity, it resists the initial force and rebounds effectively even under excessive strain. To find the Young's modulus, the stress must be divided with the strain of the specimen after a tensile test. The second step is the development of 3D models for infill density and wall perimeter tests. As research done in the literature review, ASTM D638 Type 1 is chosen as the base model due to its ideal size. All the 3D models were created with the CATIA V5. After the 3D model are done, they need to go through computational analysis. There are 2 software used to do this step, which are the CATIA V5 and the abacus. The CATIA V5 has a simpler approach of the static analysis and less step is used. On the other hand, the abacus has a more in-depth approach of static analysis. It has more steps that need to go through to carry out static analysis, but result in more detailed data of the analysis. After computational analysis has done, it is time for 3D printing of the specimen using the 3D printer that is available in the UITM. Next, after all the models have been printed, it needs to go through experimental studies. The 3D printed specimens need to go through tensile tests using the testing machine available in the UITM. When the experimental study has been done, gather the data. Compare and analyze the data gathered from computational analysis with the experimental analysis. The final step is to make a report. Gather, analyzes all the data and document it in a proper format for future references by other people. For the preliminary results, these are the data acquired from abacus of the static analysis that were run on a 100% infill density model. The model had been clamped at one end and has been exerted distributed load on a 10 km at the other end. The table is the raw data that has been acquired from the abacus. The data were transferred to Microsoft Excel and represented in the form of a line graph. Through the line graph, it is easy to analyze the pattern of the data, whether it increases linearly or drops suddenly. These are the 3D models for the infill density test that have been created so far. The parameters were shown earlier in the scope of study. And these are the 3D models for wall parameter tests for 1 mm, 2 mm, and 3 mm. Before I end my presentation, I would like to show my planning in the form of Gantt chart for the FYP1 from the start up until this point. And that brings us to the end of my presentation. I would like to thank you for your time and attention. Thank you.